All right, welcome back to the classroom. We have another sort of exam explained, not exam explained, but calculation problem here. This is from the Mass on a String lesson. It's a bonus question on banked roads. So let's have a look at what the question is and also do a bit of revision on banked roads. All right, so let's firstly just compare the pair between a car that's trying to do a curved bend on a flat road and that for a banked road. Now, for the scenario we use for the flat road, we say that the contributing factor that causes the centripetal force is friction force, static friction force on the road as the car is turning. For a banked curve, we generally ignore friction, but the question we're going to go through, and it's a more complicated one, is what if friction was involved? This is only one example, and that's just to cover if there is questions that does include friction. If there isn't, then that's awesome, but sometimes it might occur. We have the normal force pointing up like so. We have the gravitational force pointing down. The contributing factor for the centripetal force for banked road is the horizontal component of our normal force and also a horizontal component of our friction force. So let's have a look at the question we need to tackle. Okay, so we have a car that is 2,000 or 1,280 kilograms, goes around a bend at 12 meters, has a sideways friction of 16,400 newtons. What's the maximum constant speed at which the car can drive at without skidding off? Remember, because the centripetal force will be constant in these scenarios we look at, if our speed was to increase, a greater acceleration or force needs to be applied to keep the object in that circular motion, as we showed in one of the simulations. If that wasn't kept, then obviously it will expand its radius and it'll skid out of path. So let's go through this calculation. We're going to go through A first, and then we'll go through B on a different slide, just because it's going to actually take quite a lot of calculations. Okay, so the next one we have, or what is the road, or what is the speed if the road was not banked? Now, in this case, our friction force is the contributing factor for our centripetal force. Okay, so I can equate the equation as the value of my friction force equals to the centripetal force. If I do my substitutions, this is how I'll get everything together. Move everything to each side, and I'll get something looking along the lines of this. Okay, now square root both sides, and you'll find that the velocity is roughly 12.4 meters per second. This one is relatively straightforward. It's mostly substitution and finding where the correct formula is placed. We'll go to now the banked angle. And in reality, if this was a scenario where we didn't need to consider friction, the calculations would be relatively straightforward. But because we are considering friction, things get quite complicated. So let's see if you can try and solve it as well. So the net force on an object that's on a bank curve, like so, that's our centripetal force. That's also our net force. So there's two things we take into account originally, the weight force and the normal force. But we also have our friction force to look into. So let's have a look. So the net centripetal force is going to equal, all right, the F normal component, horizontal component. So do it in colors later on. And we also look at the horizontal component of our friction force. So it's this bit going along from our normal force, and also this component coming along from our friction force. We have theta, which is 10 degrees. So we have all the necessary information. It's just going to be relatively long because of the type of calculations we need to include. Okay, so firstly we need to find normal force. Now we can't work that out because you know, it's a component of the gravitational force. So we need to work out this component first. Okay, so theta's here. So to find this line of the component, you need FG cos theta, because that's the adjacent side. Okay, so our part of the F normal is going to be FG cos theta, but another part is actually from the normal force as well. Now that might sound very strange to some people, but the reason why we need to add that normal component on as well is because this friction force, if you actually have a look, also has a y component. So that y component is also contributing to our gravitational weight force. Okay, so it does make things quite complex in that sense. All right. Okay, so the gravitational weight force actually takes into account also components of our friction force, because we're looking at the net force pushing down, and that will affect the total amount that's pushing down in general as well. So our weight force is not only mg, but it's also a component of our friction force, which is sine theta. Okay, so here we have 2,800 times 9.8 plus our friction force times the sine 10 component, and that gives us, let's quickly have a look, about 15,391, call it 92, roughly around that margin there. So that's the total force coming down, okay? And now that we know the total force coming down, we can now consider the component of that downwards force. Okay, so it will be 15,392 cos 10. And I'm using the original number of the answer, so not the rounded off one that you can see there. So it might slightly differ if you write that number down. But cos, and we get a value of our normal force to be roughly 15,158 newtons. So that's our normal force. We can substitute here to find the normal component. So you can sort of appreciate how many steps it actually takes to do these questions when friction is involved, which is sort of why I would highly doubt that they ask that many, or if any, in the actual HSC. Okay, so that is the values that we're using there. Okay, so let's now substitute all this into the equation, and that will give us our centrifugal force. But remember, we're not just trying to find centrifugal force, we're trying to find velocity as well. So this question is far from over. Okay, so the overall centrifugal force, net force we have is 18,783, around about that. approximately around that. And so now we need to find the velocity from this value here, from this value there. So rearrange everything and we'll find, and again I'm running out of space, so I'll do the rest of the substitutions on this side. And as you can sort of appreciate, doing actual calculations that involve friction on a bank curve is actually incredibly strenuous. So again, I'll stress this is more like an extension type question. Our velocity is what we're trying to find. Our radius we already have. Okay, so v squared is equal to 1812. Give myself a bit more space next time, surely. Okay, so let's do our substitutions. And we find the velocity is around about 13.3 meters per second on the banked road. Oh, that took quite a bit of time, but hopefully that gives you a nice explanation of how to solve those kind of questions. Alright, and I take you back to this slide on this video. It just again goes through this calculation question that we have here with the mass string. If you found this video useful in explaining really difficult questions, really difficult calculation questions, give this video a like immediately and subscribe if you haven't done so already. I'll see you next time. Take care and have fun.